Welcome to 201D Part 4. Now, since we know what an inductor does inside a DC circuit, we're going to see what changes as soon as we put the inductor into an AC circuit. We have to remember that the primary difference between an AC circuit and a DC circuit is that the AC circuit has constant change. We are always changing the value of both voltage and current. This also means that my inductance that I find inside my coil is also constantly active. What this does is it creates a more overall opposition to the current. So now, with my AC circuit, I can no longer use the formula current is equal to voltage divided by resistance. This will no longer give me my max current, and we're going to discuss how that works. Let's start by reviewing some of the terminologies that we have with inductors. First of all, inductance is a property of an inductor to create a counter EMF within the coil. This counter EMF is what creates that opposition, and it is only present whenever the current is changing. Of course, in an AC circuit, my current is always changing, so I always have inductance. The opposition to the change in current is called inductive reactance, which is measured in ohms and represented by XL. In a DC circuit, this didn't really matter to us very much because the only time that we saw any inductive reactance is when we first started that circuit and we had our current rise. After our current reached a steady value, we no longer had inductance. Therefore, we no longer had any inductive reactance, and we could rely on resistance for the rest of our properties. With an AC circuit, we find that inductive reactance becomes a primary type of opposition, which means that we have to account for it in every step. If we were to compare an inductor in a DC circuit and in an AC circuit, this is what we would find. Inductance occurs in both types of circuits. However, in a DC circuit, it only occurs when the circuit is first initiated or when it's opened up again. In an AC circuit, since we have constant change, inductance is always constant. Inductive reactance is dependent directly on inductance. So therefore, if I always have inductance inside an AC circuit, I also always have inductive reactance. What we find is in a DC circuit, the inductive reactance is what is limiting the rise to the fall of the current. However, in an AC circuit, it now becomes the limitation for the total current. That brings us to maximum current in our circuits. In a DC circuit, we found that the maximum current was only limited by the circuit resistance. If I had a pure inductor with no resistance, I'd find that there would be no limitation to my current. It would constantly rise until something burned out. However, in an AC circuit, since I always have inductive reactance and I have the resistance of the coil itself, I have to take into account both resistance and the inductive reactance, and they're both affecting the total current. If I had a circuit fed by the same voltage, one in AC and one in DC, and I had the exact same coil in both the circuits, what I would find is that my maximum current in the DC circuit would actually be higher because it's only limited by the resistance, whereas in my AC circuit, it's being limited by my resistance and my inductive reactance at the same time. Therefore, total current in an AC circuit compared to a DC circuit of the same value will always be lower in the AC circuit. There are two different factors that affect the amount of inductive reactance inside a circuit. We've already discussed how inductance and inductive reactance are directly related. Therefore, it's easy to see that when I have more inductance inside my circuit, I should also have more inductive reactance. The reason for this is the higher my inductance is, the higher my counter EMF is going to be, therefore the higher the opposition to that current change is going to be, which is how I'm measuring my inductive reactance. The other factor that's going to affect how much inductive reactance I have inside my circuit is my frequency or my rate of change. It stands to reason that the more change I have, the more opposition I need for that change. So when I have a higher frequency circuit, it creates a greater counter EMF, which gives me more inductive reactance. We can put all these factors into a formula. XL is equal to 2 pi FL, where XL is my inductive reactance, F represents my frequency, L represents my inductance. The 2 pi is there because we're actually graphing a curvature. When we analyze this formula, we can see that both frequency and inductance are directly related to inductive reactance. And if I double one, I should double the other value as well. Let's use the formula to analyze this circuit. We have a source of 120 volts at 60 Hz, which is fairly typical for us. We also have a coil that has 28 ohms of resistance and 0.8 henries of inductance. Keep in mind that no coil is a perfect inductor, so we will always have measurable resistance within our coils. We can put our circuit values into this formula. We end up with 2 times pi times a frequency of 60 times an inductance of 0.8. The result is 301.6 ohms of inductive reactance. We can also now see how the inductive reactance is a major form of opposition to current inside this circuit. If we take the exact same circuit and just change out our source to 347 volts and at 180 hertz, we'll find that our inductive reactance is going to change as well. The voltage doesn't matter because voltage is not part of the formula. Therefore, voltage itself will not affect the total XL value. However, the frequency will. If we put our new frequency into our formula, 2 times pi times 180 times 0.8, we find now our inductive reactance has increased to 904.8 ohms. Now, while you have your calculator out, you should also be able to determine the fact that since I tripled my frequency, I've also tripled my inductive reactance. So we can see that there's a direct relationship between frequency and inductive reactance. Now that we've seen what the effect of changing the frequency has on our total inductive reactance, we're going to see what happens if we swap out the coil. We've now changed our coil out for one of half the value, so we have half as many turns. I can tell that because my resistance is halved, as well as my inductive reactance is halved. If we put this into our formula of 2 times pi times our frequency of 180, because that has not changed, times our new inductance of 0.4, we find that our total inductive reactance is now 452.4 ohms, which, if you do the math, you'll find that since my inductance is halved, my inductive reactance is also half. So we can see how there's a direct correlation between my inductance and my inductive reactance as well. You've now come to the end of 201D Part 4. Make sure you are reviewing the principles that we talked about in this video and you understand the correlation between inductive reactance, inductance, and frequency. Also make sure that you understand the difference between an AC circuit and a DC circuit and why the frequency is making such an impact on our total circuit values. Once you've done that, do the worksheet that I have for you in Blackboard, as well as the knowledge check, and then continue on to Part 5.